Okay, I'm going to get started. Wanted to begin with an announcement about Test 1. So Test 1 is next week. It's next Thursday. So before we got Test 1, we've got today's class, this Thursday's class, and next Tuesday's class. So it's three lecture classes, then Test 1. Test 1 will be in here. It'll be for 1 hour. It contains 3 problems that you'll fully work out. So 3 problems where you've got to write down all your equations, your diagrams if you need them, your calculations to solve those problems. And then it contains 20% true-false. It'll be 10 true-false questions. So that's the format of Test 1. There's a practice test that's online. You'll explore that in Monday's recitation class. There's a formula sheet that comes with Test 1. There's a copy of that on Canvas. The material on Test 1 is all the material that we will have covered up to Test 1. So it's all the material on electricity. It's all the material on electrical charge and electrical forces and electrical fields and electrical flux and electrical potential. And then the work we're doing now on electrical circuits involving capacitors and resistors and batteries. Any questions on all that? Yes. Oh, yes, sorry.
Can we expect the homework and the tests to kind of have the same type of problems?
The intent is that, yeah, the homework is practice for the problems on the test. The lecture quizzes are practice for the concept questions on the test. The worksheets in recitation are meant to be practice on the for the problems on the test. So that is absolutely the intent, and the intent is to cover this material here. I think if you look at a practice test, then you'll see, you know, to your eyes, you know, how closely is it related to what you've done in the homework, what you've done in lecture quiz and so forth. Because obviously it's not going to be the same problems, but it's going to be those types of problems. Yeah.
Thank you.
Any other questions? Okay, I'll remind you each class, so Thursday and next Tuesday. So if you have questions, you can always ask them then, or you can always just email me, of course. Okay, let's get on with today's class. So in today, I want to talk about electrical current. Really, the whole class is about electrical current. I want to talk about visualizing, conceptualizing electrical current. We'll visualize it, conceptualize it at kind of a macroscopic, big picture level. We'll visualize it, conceptualize it at a more microscopic level. Those will be our first topics. Then I want to talk about the Ohm's law, resistance, resistivity. That's really about electrical currents and the quantity of electrical current that flows. And then finally we'll talk about electrical energy and electrical power, because electrical current conveys electrical energy and electrical power. So in that way the whole class is about electrical current, which is flow of electricity, which is flow of charge. So there's an important point here. In prior class, we talked about conductors, and in this class, we're going to talk about conductors, because circuits are made of conductors. In the prior classes when we talked about conductors, we talked about them in equilibrium. And we said that conductors were kind of this landscape of zero electrical field and constant electrical potential when they're in equilibrium. In today's class and the next 3 classes, our conductors aren't in equilibrium. So they're not landscapes of zero electrical field. They're not landscapes of constant electrical potential. They're in what we call steady state. In steady state, charge is flowing through the conductors. Electrical current is flowing through conductors. That's not equilibrium. That's steady state. In steady state, there is an electrical field in general in the conductor, and there is a electrical potential hill, not a constant electrical potential in the conductor. So that's an important difference about steady state conductors from equilibrium conductors that we're meeting for the first time today's class. Okay, so we're going to talk about really a rather basic circuit in today's class. We're going to talk about it from different perspectives, from different viewpoints. I've sketched the circuit here. It's kind of really in evolution, in circuit evolution. It's the primordial circuit. It was the most basic circuit, and you know it's basically, you know, iPads and iPhones are just more sophisticated versions of this basic circuit. So here's the circuit. We have to thank a Italian scientist, Volta, for this circuit, and we have to thank him also for like iPhones and iPads, because all the circuits we're going to be talking about have batteries inside them. This circuit has a battery, and the iPad and the iPhone and whatever, everything has a battery inside it, and that's key to the operation of the circuit. So we've got to thank Volta for these circuits. Batteries allow electrical charge to continuously flow, to freely flow around electrical circuits. So in this circuit here, it's the battery in the circuit that constantly allows electrical charge to flow through a circuit. It's the battery in an iPad or an iPhone that allows electrical charge, current to flow constantly around those circuits. If Volta hadn't invented the battery, the way we would have had to get charge to flow from one place to another place is by rubbing something, like rubbing the cat's fur on the glass rod or the silk on the rubber rod, and that would be exhausted. And so, you know, the invention of the battery was a landmark event in that it freed us to have electrical charge, electrical current flowing constantly, continuously through electrical circuits. You know, in a way, it's a bigger discovery than the internet. You know, to be able to make a battery that could power, you know, a circuit, a simple circuit like this one, or a more complicated circuit like iPad or iPhone. Okay, so this circuit here, the primordial circuit, it contains the battery. It contains a resistor, which in this case is just a lamp or a light, and we'll say what a resistor really is. And the circuit is completed by making a complete circuit loop with this wire on the left and this wire on the right that connects the terminals of the battery, the positive and negative terminals of the battery, to the terminals of the resistor, the 2 terminals of the resistor. Okay, here's how we might sketch that circuit. Upstairs here, remember, is a notation in a circuit diagram for the battery. There's a positive terminal, a more positive potential on a battery. There's a negative terminal, a more negative electrical potential on a battery. And this is how we symbolize that. Remember, you can, this long arm here, you could imagine cutting that in half making the plus sign. The short arm here is too short to cut in half and make it, so this is a minus sign. Anyway, these are the terminals, and here's the symbol for a resistor. It's this zigzag. And this zigzag, I don't know who invented the zigzag for the resistor, but the way I think of it is the zigzag for the resistor, because for the charge to flow through the resistor, the current to flow through the resistor, it's not so easy as flowing through the wire, flowing down the copper wire. And so it's got to do a bit of work going through this zigzag. And so we'll see that later on, that the resistor kind of inhibits the motion of the charge or the current as it flows through the resistor, like the lamp is a resistor. There's two ways that we tend to think about this circuit, this simple circuit, or any more complicated circuit. One is from a kind of force perspective. In the force perspective, the battery is kind of pushing the charge around the circuit. So there's some sort of force coming from the battery that's pushing the charge around the circuit, making the charge flow around the circuit. And then the resistor in the circuit is causing some drag, some kind of resistance on the path of the charge around the circuit. And so from the force perspective, there's the battery pushing away, that's a force, and the resistor, that's kind of resisting, that's sort of a frictional force as the charge flows, as the current flows around the circuit. That's one perspective, we'll talk about that sometimes. The other perspective is an energy perspective. In the energy perspective of the electrical circuit, the battery, the battery is kind of a source of energy. It's chemical energy, but it's a source of energy. And the resistor is something that's dissipating energy, actually turning energy into heat. And the way the circuit's working in the energy perspective is that energy is flowing from the battery, chemical energy. That's the source of energy. It's flowing to the resistor. That's dissipating the energy, producing heat. And the circuit is really just the path around which that energy flows from the battery to the resistor. And so that's the energy perspective on the circuit. So let's start to talk about electrical current. Electrical current, just to be clear, is a measure of the flow of charge. It's a measure of the movement of charge. It's a measure of the flow of charge in our electrical circuit, the movement of charge around our electrical circuit. It's how we quantify electrical charge flow. It's given the symbol I, symbol for current. It's measured in coulombs per second, charge per second, which we abbreviate to amps or amperes. So that's the units of electrical current. So I'm going to show you some metaphors or analogies or whatever the right word is today. We can't see electrical currents, so we have to imagine electrical currents, and so we use analogies to electrical currents. The analogy that we often use to electrical currents that we can't see is a flow that we can easily see. If we walk into nature, we might see the flow of water down a river, or the flow of water down a creek, or the flow of water over a waterfall. And that's going to be our analogy. So here's the water current analogy of the electrical current in a circuit. Here we are, we've gone out into nature, we're looking at this nice waterfall, and we can think of it in terms of an electrical current. See, the water is flowing over this, down the waterfall from some higher gravitational potential energy to some lower gravitational potential energy. There's a gravitational potential energy difference. And the water current, which quantifies the water flow, the amount of water flow, is simply defined as the mass of water that flows down the waterfall per unit of time as we measure the water flowing down the waterfall. So we're seeing here water current. we're seeing the amount of water that flows per unit of time. We would measure it in kilograms per second. We do the same sort of thing for electrical current. So here's a picture of electrical current. Now in this picture, in the next picture, I've turned the waterfall on its side. So now it's over here on the left-hand side. That's a higher electrical potential, a higher electrical potential energy for positive charges. So this would be the top of the waterfall. It's over here on the right-hand side that for the positive charges, this is the lower electrical potential energy. This is the lower electrical potential. So this is the bottom of the waterfall. This is like I've connected the positive terminal of the battery over here on the left, the negative terminal of the battery over here on the right. What you're seeing is not water flowing from left to right, like in the waterfall picture. You're seeing charge flowing from left to right. So I've actually depicted individual positive charges, whoever they are. I don't know who they are, but I've pictured those individual positive charges streaming from over here on the left to over here on the right. They're rolling down the electrical potential hill. They're being repelled by the positive terminal on the left, attracted by the negative terminal on the right. We can quantify the amount of charge that's flowing left to right, the current, electrical current that's flowing left to right, by introducing, in analogy with the water current, an electrical current. And here's the equation for it. The electrical current here is the amount of charge, delta Q, that flows past some point in some time interval, delta T. So this is a number of coulombs per second, an amount of charge per unit of time. And this is how we think of electrical current. Now this picture, there's been some big mistakes in physics over hundreds of years. Here's probably one of the bigger mistakes in physics. In wires, in conductors, it's electrons that are flowing, that are the cause of the current, the cause of the flow of charge. It's not positive charge carriers that are the cause of the current, the flow of the charge. So this picture is misleading, and I've got, I'm imagining a wire, and I've got positive charges streaming from the left to right. But in a real wire, it's actually negative charges that are streaming through the conductor. So that's a minor mistake, or a big mistake, depending on your perspective. That was made to call electrons negative. It would have been handier if we called them positive, but we did call them negative, and nobody can change it now, right? It's worse than Britain driving on the left-hand side of the road and trying to change that now. We can't change this now. Electrons are negative. So in a real wire, in a real wire, made of real metal with real electrons that have real negative charge inside them, this is actually the situation for the electrical current. Over here on the left-hand side is still the positive terminal of the battery. Over here is still the attached to the negative terminal of the battery. Over here on the left-hand side, this is still higher electrical potential, and this is still lower electrical potential. But for an electron, this is lower electrical potential on the left-hand side. That's the reverse of the positive particle case. For an electron, this is higher electrical potential energy on the right-hand side. That's the reverse of the case for the positive particle. The electrons stream up the electrical potential hill. They stream up the electrical potential hill, streaming from higher electrical potential energy of each electron down to lower electrical potential energy. They're being repelled by the negative terminal, attracted by the positive terminal. So this is the real picture in a wire. This is the real picture, say, in a copper wire. The current size is still defined by this equation, the amount of charges carried by the electrons per unit of time. But the direction of the current, because of this mistake, is defined as the opposite direction to the motion of the electrons. The electrons, negative charge particles, are traveling towards the left in this picture. The current, what we call conventional current, is traveling towards the right, the opposite direction to the electrons. It's the direction that positive charges would move if such things were moving in an ordinary piece of copper wire. Okay. So that's defined current. Now let's talk about a more microscopic perspective on electrical current. Because I've already said that current is actually tiny little electrons that are streaming down the wire. And actually, if you think about it, the water over the waterfall is really at a microscopic level, little H2O molecules that are falling under gravity from the top of the waterfall. So let's talk about electrical current at that level. I'm going to introduce this formula here, which is meaningless to us right now, but by the end of the next couple of slides, that will be meaningful to us. So that's the purpose of these couple of slides, or few slides. Here's, obviously I didn't pay enough for the pixels on this slide, but this is meant to be a picture of water flowing. I don't know, we've gone for a walk in the woods, there's a stream, and we're looking at the water flowing along the rocky stream. And what's the point I'm making here? Well, this water flow is a metaphor for electrical current flow, for charge flow. But in this case, this water flow, you can see it's been impeded by the stones and the pebbles and the rocks in the stream. The same thing happens when charges, electrons, flow through a metal wire. That flow of electrical current is actually impeded. It's not impeded by stones or rocks or pebbles inside the metal. It's impeded by all the different ions that are inside the metal, the positive ions. So we can take this analogy beyond just the flow of water or the flow of electrical charge to things impeding the flow of water, like rocks and pebbles, to things impeding the flow of electrical charge in metals, which is the positive ions in the metal. Okay, so we're going to think about that a little bit. And we're going to go back to our picture of, remember, the electrons flowing through the metal. Here's a picture of an individual electron that's flowing through the metal. This time, just to confuse us further, I put the negative terminal of the battery over here on the left. And I've got the positive terminal of the battery over here on the right. And I'm watching this single electron. It's being repelled from the negative terminal because like charge. It's been attracted by the positive terminal because it's opposite charge. And I'm watching its path through the metal. And it corresponds to some current, I pictured it here, due to this flow of charge from the left to the right. Now, if you were to look at it, supposing you could really do this, you could really look at an electron flowing down the wire. Supposing this is the wire, I'm the electron. Am I just walking across like this as I flowed calmly, walking down the wire? No, I'm not. No, the electron is not. The electron is in some crazy random motion. It's bouncing around all over the place. It's rattling around inside the wire. And there's this rattling random motion, but superimposed on that is a sort of gradual glide down the length of the wire. So if you were able to look at an individual electron flowing down the wire, the first thing you would spot is just going everywhere. It's randomized motion. But superimposed on top of that is a little gradual glide from the left to the right in my picture. That's what I tried to imagine here. Look, this electron is bouncing off positive ions that are impeding its flow all over the place. Sometimes it's going left to right, sometimes it's going right to left, sometimes it's going up and down, all sorts of random motion. it takes a long path just to travel this short section of wire. It's rattling around, but gradually drifting. That drift is called drift velocity. That's the velocity that causes the electrical current, that causes the flow of charge. That drift velocity is superimposed on random velocity, random motion. There's an equation that relates the current flow down the length of the wire to that drift motion along the length of the wire. We said that the drift motion is actually the cause of the electrical current. So the drift motion is related to the electrical current. And that relationship, that equation, is on this slide here. I've written it down here. Okay, so let's just talk about the quantities that are in this equation. On the left-hand side is the current. So this is going to be an equation for the current in terms of the individual electrons that collectively make the electrical current. N, what's that little lowercase n? That's how many electrons there are that are free to move inside the conductor, the copper or the aluminium wire, per cubic meter. So that's sort of a measure of how many electrons we've got. How many electrons we've got per cubic meter. The bigger the n, the more the number of electrons that are free to move, the more the current you get. E, that's the charge that each of those electrons carries. So there is a current because each electron carries a certain amount of charge. And so it's obviously the current is going to depend on the electronic charge. If we made it so, like if I could wave a magic wand, make it bigger, then we get more current. If I could wave a magic wand and make it smaller, I get less current because I would have changed the charge that's owned by each of those individual electrons that's free to move. V subscript D, to discriminate it from the other random motion, V subscript D is the drift motion. This is the thing that's causing the current. The fact that electrons not only are randomly moving around, but they're gradually drifting from left to right in my picture. And then A is the area of the wire, the cross-sectional area of the wire. So it might seem intuitively obvious that if you have a sort of big, fat copper wire, that can a lot more current can pass through that. If you had a very thin, slender wire, less current could pass through that. There's more room in the big wire, there's less room in the thin wire, and that's reflected in the equation here. So this is the sort of master equation for connecting that concept of electrical current being the flow of charge to the understanding that that flow of charge is due to individual electrons drifting from the left to the right. Okay. Let me give you a little analogy, another analogy. Like we said that one analogy to electrons flowing through a metal, something we can't see, was water flowing in some creek or some stream across boulders and rocks and whatever. So that's one analogy. Another analogy is the bed of nails. So the bed of nails, we've got a bed of nails here. That's an analogy, a metaphor for all the positive ions that are inside a metal wire. So if you could look inside the metal wire, you see this massive, absolutely massive array of positive ions. They'd actually be really regularly arranged. So it would look like this. I've got some electrons. I've got some metaphors for electrons. They're tiny, you can't see them, but they're tiny yellow ball bearings. So these are my metaphors for the electrons. And I'm just going to, under a gravitational potential rather than an electrical potential, let some electrons flow through the wire. Now, you notice that they, as they flow through the wire, they didn't just fall straight down the wire. Rather, they underwent this kind of random motion as they bounced off the ions in the wire. and they gradually drifted through the wire. I mean, not too gradually, but they're sort of drifting more than accelerating. And that's an analogy to how electrons move through the wire. Another analogy is kind of raindrops or snowflakes. When I came in yesterday, it was snowing. I was looking at the snowflakes, and of course, what am I thinking about? I'm thinking about, oh, well, that's a wonderful analogy for electrons in a wire, right? All those little snowflakes, they're not under gravity accelerating towards the ground at ever and ever increasing velocities. Rather, they're drifting towards the ground because they're interacting with the air that's causing a drag, just like the ions cause a drag. And that's why you see snowflakes just drift towards the ground rather than accelerate like some cannonball towards the ground. It's why you see raindrops. Raindrops don't keep accelerating towards the ground. They gradually drift towards the ground. Again, because there's a resistance to their flow towards the ground. It's air resistance. Okay, let's do a little calculation to get an idea of what the drift velocity is. So in this question, we're told we've got a 200 kilometer long cable. It has 4 centimeters diameter, so 2 centimeters radius. We're told it's carrying 1,000 amps of electrical current. I mean, that's a very long cable. It's a very fat cable, and it's carrying an awful lot of current, 1,000 amps. How did I invent that? That's how electrical current is carried around the nation by the power grid. It's carried by long cables like this cable, that are big fat cables like this cable, that carry really large currents like this 1,000 amps. So this is not some imaginary fictitious situation. This is real life electrical currents being carried by the grid. What we're going to do is calculate the speed that a electron, if we could peek inside and see an electron, how fast is that electron drifting down the wire? How long did it take that electron to drift that 200 kilometers from the power station to your house? How long does it take? Okay, so let's see if we're capable of calculating that. I want to go back to this equation. It's going to be my starting point, that I equals N.
Dr. Goring, we can't see you.
Oh yeah, thank you. That's not the first time that's happened, by the way. Here we are. Now we can't see me. Okay, I'm going back to this equation. I equals NEV subscript D times A. On the left-hand side, electrical current and notion of electrical current as flow of charge. On the right-hand side, our understanding in terms of individual electrons streaming down the wire with some drift velocity and some number of them, some swarm of them. We want the, if we want to find the velocity of the electrons down the wire, we just need to rearrange this, don't we? It's not too hard. Apparently it is. Current divide the drift velocity will be the current divided by N, E, and A. Now, we were given the current in the problem. So we were told that there was 100 amps of current flowing down the wire. We were given the radius or the diameter of the wire in the problem. So actually that meant if we do pi r squared, we know the area of the cross-sectional area of the wire. We remember, because we've taken chemistry, the charge of an electron, 1.6 times 10 to the minus 19 coulombs. Finally, there's an n. That's the number of electrons inside the wire that are free to move. That number you have to look up. So I went to the textbook and I said, I've got a copper wire. I've got to look up in copper. So it depends on the nature of the wire. In copper, how many free electrons are there that are able to, per cubic meter, flow down the wire? And if you look that up, that number's about 8 times 10 to the 28 per cubic meter. So it's this huge number, 8 10 to the 28 per cubic meter. So everything on the right-hand side of this equation is known to me. I just got to plug all these numbers in. So we can just do that. 1,000 amps. I've got to divide by this ridiculously large number of electrons inside a cubic meter of wire. I'm going to, yeah, let's put the units, should do that. Electronic charge, 1.6 times 10 to the minus 19. I'm not going to worry about the fact it's negative. That determines which way the electrons are going to move. Finally, the cross-sectional area, I worked out pi r squared already, so that was 1.26 times 10 to the minus 3 meter squared. And if I multiply and divide out all these annoyingly large or small numbers, I get the speed of the electron, and the speed of the electron comes out to be remarkably small. It's 5.8 times 10 to the minus 5 meters per second. Gosh. You know, I thought I was slow. But this electron is really slow. It goes, you know, it's 6 times 10 to the minus 5 of a meter. That's 60 microns. That's a tiny, tiny distance. That's how far an electron goes in a second. Already we know it's going to take a long time to get the length of the wire if it only goes that sort of micron level distance in one second. Okay, so the second part of the problem is how long does it take to go the length of the wire? Well, there's a second equation that we can use. I'm going to think about speeds. The speed, what's the definition of the speed? It's the distance that you travel divided by the time that you took. So that's from physics 211. I know the speed I'm traveling at. I know the speed the electron's traveling at. I know the distance the electron's got to travel. I want to figure out the time. So the time that the electron will take to go the entire length of the wire, if I just rearrange this definition of speed here for the time, is going to be the distance that it's going to travel. It's the length of the wire in my example, divided by the speed that it travels at. So the distance was 2 times 10 to the 5 meters. The speed that it was traveling at was this ridiculously small 58 microns per second. And if I divide one by the other, I get something that is the scale of 10 to the 10 seconds. I put it in years, actually, so I converted it to years. It's 110 years. Gosh. So that electron that just left, I'll be dead before that electron gets from the power station to my house. Those electrons traveling down that wire are traveling extremely slowly. The reason that there's a big electrical current is there's so many of them packed into the wire. There's 10 to the 28 per square meter. Anyway, that's just to give you an idea that the drift velocity of electrons in conductors is actually incredibly small. And it's just the fact that there are so many of those electrons that you can get currents, large currents. Okay. Am I going the wrong way? What am I doing? No, I'm not going the wrong way. Ohm's law. Ohm's law, resistance, resistivity. Yeah.
Going back on the previous
Yeah.
example, do you think that like the electrons repelling each other also contribute to the flow rate?
That's actually a very, very good question. And I think my answer would be absolutely they do. Supposing you had this long length of wire, 200 kilometers, and there's these electrons at this end, the left-hand end. They start to move in a little bit. Well, what are they going to do? They're going to push on the ones that are next to them, which push on the ones that are next to them, which push on the ones that are next to them, and that's why something comes out at the other end. So that's actually a fantastic question. I like it. So yeah, that's the reason, you know, if you just imagine walking slowly in on this end, why would something come out at the other end? It's because everybody's pushing on everybody else and pushing down the length of the wire. It's just like you had a long queue of people, right? You start pushing at this end to get into the nightclub or whatever I'm going to, then the people at the other end of it start falling in the nightclub. Not that I go to nightclubs but anymore. Okay. Why do the electrons flow down the wire? Like, why did the water flow over the waterfall? Well, the water fell down the waterfall because of gravity. The electrons flow down the wire because of electricity. There's a gravitational force that's causing the water to fall over the waterfall, and there's an electrical force that's causing the electrons to stream down the wire. So that's the answer. Can we write a relationship? Can we find a connection between the amount of current that flows down the wire and the electrical force or the electrical potential that's causing it to flow down the wire? And of course the answer is yes, otherwise I wouldn't be posing the question. So there is a simple relationship between the cause and the effect here. The cause of the electrons flowing down the wire is that there is an electrical force or an electrical potential, and the result, the effect, is that current charge moves down the wire. So what's the relationship between those two? Oh, gosh. Still can't get the one I want. Come on. The relationship was figured out by a scientist called Ohm, George Ohm. What he did was, you know, once Volta invented the battery, everybody is passing electrical currents through every possible stuff of all sorts of length of it, all sorts of cross sections of it, and exploring this world of electrical current flow or charge flow. What Ohm did was systematize it, ordered it. What he discovered is, and let's take a look at this graph, is that if you apply an electrical potential to some material, you'll get an electrical current that's through that material. So that material might be a cylinder, say, of copper, or a cylinder of aluminium, something that's an electrical conductor. When you apply a potential to it, you get a current through it that's in proportion to the potential you apply to it. So if you double the potential across the copper, you'll get twice the current through the copper. If you half the potential, you get half the current. That is that the current is in proportion to the potential, which sort of makes sense. That kind of cause and effect sort of makes sense. So, you know, if you had no potential, you get no current. If you apply a little potential, you'll get a little current. If you apply a lot of potential, you get a lot of current. So that's what he discovered. And that relationship is called Ohm's law. I've written it up here. So the current is in proportion to the potential difference between the ends of the wire or the ends of the sample. There's a proportionality constant. It's called resistance. and it's given this symbol uppercase R. So this is just the proportionality constant between the current that flows and the potential that's supplied. The way the resistance works, if something has, look at the equation, something has a big resistance, that means it actually is resisting the current a lot. So big resistance means a certain potential will only give a small current. If something has a small resistance, which means it doesn't resist current flow much, then you apply that potential to that small resistance sample, you'll get a lot of current. So that's why resistance is in the denominator in this equation for the current due to a applied voltage. Often we don't write the equation as I equals delta V divided by R. We often denote it the more familiar way that you know, V equals IR. That's the same equation. We put the cause, the V, on the left-hand side, and the result, the current, on the right-hand side. So we're sort of playing a little bit with how the thing works in terms of cause and effect. Also, we're dropping the delta V because I can't keep being bothered to write delta V's for everything. I'm just going to drop the V, and we're just going to know that it actually means the potential difference between the ends of the wires. So often, normally we would write it as V equals IR, but the way to think of its discovery and how it works is really that the current is in proportion to the potential difference between the ends of the wire divided by this characteristic of the wire, resistance, which is how much it resists current flows. That's how we think of it. I can show you a demonstration of this. So on the 2 meters that you can see, I'm going to put it on the camera just in case that helps. Doesn't really help. just makes it worse. But give me 20 minutes, I'll get it set up. I got a power supply over here on the your left-hand side. Then I've got 2 meters. One's reading current and one's reading voltage. The power supply is supplying current and applying voltage to this is a resistor. So it's applying a voltage to this resistor, and there's a current flowing through this resistor, and the meter on the left is reading the voltage, and the meter on the right is reading the current. Now what I'm going to do, I'm going to come over here now, obscure other people's views. I'm going to change the voltage that I'm applying. So I'm going to change this voltage that's read on this meter. And you're going to watch that current on that meter. So if I decrease the voltage, I correspondingly decrease the current. If I increase the voltage, I correspondingly increase the current. And that's simply Ohm's law. That the amount of current, the amount of flow of charge is in proportion to the potential hill that you give it to roll negative electrons roll up the potential hill. So that is simply Ohm's law. Okay. we talked about resistance, the resistance of a sample of material to current flow. It could be a wire, it could be a slab of material. There's also a quantity called resistivity of the sample or the material. And so I want to introduce the relationship between resistance and resistivity. The resistance of, say, a wire or a slab of material is, well, think about this. I can't do it there. But I've lost, here it is. So this is going to be a picture of the relationship between resistance, resistivity, and geometry. This cylinder of material, this cylinder of copper or aluminium or whatever it is, has a certain resistance that we measure in ohms. That resistance is determined by a number of factors. It's determined by several factors. One of them is geometry, the geometry of this piece of material. The other one is the substance of this piece of material. In particular, the resistance, that's the uppercase R here, of this copper, aluminium cylinder, whatever it is given by this little equation here, rho L divided by A. L, that's a piece of geometry, that's the length of the sample, say the length of the wire. L, another piece of geometry, that's the cross-sectional area, that's the area of the wire. Rho, that's the resistivity, that's a characteristic of the substance, the material. So, the resistance of some piece of wire or some slab of material can be calculated from the size and shape of the material and the nature, the substance of the material. If you want to understand this equation here, think about it this way. Look, if you had a longer wire, what would happen? Two otherwise identical wires, but one's longer than the other one. If one is longer, so L is bigger, this equation says that the resistance will be larger. And that sort of makes sense, right? It's like you put together, a longer wire. It's going to cause more resistance to an electron moving through that longer length of wire. If you have a shorter length of wire, that's less resistance to the electron moving through the ions, pebbles and rocks in that wire. And so resistance depends on the length of the wire. When you make a longer wire, you're going to have a greater resistance. When you make a shorter wire, you're going to have a smaller resistance. Resistance also depends on another feature of the geometry, the area. The area in that equation for resistance is actually in the denominator. So if you have a big area, a big thick wire like the power line wires, that's going to have a relatively large area which will make the resistance small. There's a lot of room for the electrons to stream along that wire. It's like a wide river rather than a narrow creek. So big area means a small resistance if everything else is the same. Small area, so a very narrow wire, a very thin, slender wire, that would mean a large resistance. It's much harder for the electrons to squeeze down that really narrow stream or creek or brook or whatever we call it. So it depends on the area too. And then it depends on the resistivity of the material. So copper is famous, as you know. Copper's famous for having a very small resistivity. Current easily flows through copper. That's why, obviously, why we make copper wires. And so it has a small resistivity, which makes a small resistance when you make a wire out of it. Aluminium also has a pretty small, not as small resistivity, but we also make wires out of aluminium. Old houses have aluminium wires. That also allows current to flow much more easily. Other metals have higher resistivities, which means that current flows less readily in other metals. So these are the three ingredients: the length of the wire, the cross-section of the wire, the material of the wire, that determine the resistance of the wire based on its geometry, based on its substance. Here's a quiz. In this quiz, we got three different, I don't know if call them wires or call them samples. And we're going to compare their resistances. We're going to order their resistances. Let's see, where are we? Oh, I've got to publish it. Did I do that? Maybe I unpublished it. In this question, we got three samples, A, B, and C, on the left, center, and right. We're going to imagine a current flowing through them, each of them, from left to right. And that current flows in inverse proportion to their resistances. And we're going to compare the resistances of these three samples. They're all made of the same material. So you could imagine all of them as being copper cylinders. But they do have different lengths. So this one over here on the right is shorter. The other two, A and B, are longer. They also have different diameters, different cross sections. So this one in the middle has a smaller cross section, and the other two have larger cross sections. So we've got to rank from highest resistance to lowest resistance. So who's got the highest resistance? We'll list that first. Who's got the smallest resistance? We're going to list that last. Okay, so I'll give you a minute or two more to think and discuss it, and then we'll move on. Yeah.
So, for these types of problems, is there ever a time where you would give us, like, where the wire is changing area? Like, it's bigger in this, and okay.
Yeah, it'd be too high. Yeah,
Alright.
yeah. That's a good point.
Yeah, like a bottleneck. Oh, I mean, they're even.
Oh, sorry.
Why? B has a smaller.
Okay, let me get started again. Let's just go through the answer to this problem. We want to order the three samples from largest resistance to smallest resistance. What would make, given that they're all the same material, a large resistance? Well, one way to make a larger resistance is to have a longer length of the wire. So if we want to look for a large resistance, we're going to look for a longer length of the wire. The other thing that would make a larger resistance would be to have a small cross section, to be a thin wire rather than a thick wire. So we also want to look for a small cross section to the wire. So I'm looking at the three pictures, and I spot the one in the middle that has as long a length as any other sample and has the smallest cross section of any sample. And so that one in the middle this little guy here, that surely has the largest resistance. It's because it's as long as any other sample and it has the smallest cross-section of any other sample. Current's going to have the hardest job, the hardest task of flowing through this sample. If I wanted to look for the sample that had the smallest resistance, what would I look for? I'd look for a short wire, because that would be easy for the current to flow through, and I would be looking for the largest cross-section, because that would be easier for the current to flow through. That points me to this guy over here on the right. This is the shortest of the wires, and it's, there's no other wire that has a bigger cross-section than it. And so the order is B, A, C. So hopefully, yeah, here's B, A, C. That's the that's the ranking of the resistivities. Oh, I wanted to show you just a little video of resistivity and resistance and the relationship. Let me just do that. So, oh, yeah. In this video, you're gonna see me measuring the resistance in two lengths of wire and two different cross sections of wire. I don't know why the hamster, 1 hour of hamster videos come up next. I can't explain it. I honestly never watched a hamster video. I watched cat videos, but never a hamster. Okay, anyway, we got, I want us to look at a couple of things. Oh, I did that by accident, but it's helpful. Here's a length of wire. Here's another length of the same material of wire. I'm going to measure the resistance of this length of wire. And we're going to measure it on this resistance meter. And you can see here it's actually 1.3 ohms. Then I'm going to measure the resistance of half the length of wire. And we should see it decrease, about half the length of wire. I'm not very precise. We should see it decrease by about half. And then I'm going to measure the resistance of this length of wire, which is a thicker wire. So for this wire should have a smaller resistance for the entire length and a smaller resistance for the shorter length. So we're going to make 4 measurements, 2 lengths of wire, 2 cross sections of wire. We know how the resistance should depend on the length and the cross section of wire. Both wires are nickel, so it's the same material of the wire. So I'm kind of showing you where the contacts are. I'm measuring that length of wire. It's 1.3 ohms. And now I'm going to just measure a fraction of the length of the wire, about half it. And I'm showing you that too. And look up here, we got about half the resistance because I've got a shorter wire. So it's real. It's not, I didn't invent it. And now I'm going to move up to the wire above. This is the same length as I just measured for the wire below, but this has a larger cross section. Look, I got an even smaller resistance because of the larger cross section. And then finally, I'm going to measure double the length now. And I've roughly doubled the length. So I roughly double the resistance of the wire. So this is truly a demonstration of the geometry dependence of the okay, got it.
That's what I wanted. I want to know how it works. It's occasionally.
Last topic. I want to talk about energy and power and electrical current. So one thing we said at the very beginning of the class is that circuits can be thought of as arrangements in which energy is moved from, say, a battery to a resistor. It's supplied by the battery and it's dissipated by the resistor. And so we're going to explore that world a little bit. So the water analogy again, the water metaphor is that in a waterfall, the water starts out at the top of the waterfall with a larger amount of gravitational potential energy, and when it falls down, it's got a lesser amount of gravitational potential energy. So it's changed its gravitational potential energy. It's turned it actually into thermal heat energy. The water at the bottom, and this has been measured, the water at the bottom of a waterfall is warmer, a little warmer than the water at the top of the waterfall because of that gravitational energy being turned into thermal energy. The electrical version of this is that as current flows down a electrical potential hill, you're turning electrical potential energy, which was larger when the current came out of the battery, into less electrical potential energy when it returns to the battery. That loss in electrical potential energy that was provided by the battery has been turned into heat energy, thermal energy, inside the resistor. And so that's the electrical equivalent that we want to explore. So on this slide here, the main purpose of this slide is to introduce two equations that describe the electrical energy that's associated with a current flowing or with charge moving, and the rate at which electrical energy is supplied. That would be called the work that is supplied when an electrical current, when charge is flowing. So in this picture here, imagine that there's some battery that's connected across this length of wire to the terminal on the right and to the terminal on the left. It causes some current to flow. Let's not worry about whether that current is really electrons or really positive charges that don't exist like this. So we're flowing some current. There's some change in electrical potential energy as this current flows down the electrical potential hill. What is that change in electrical potential energy? It's given by this equation here. The change in electrical potential energy is simply the amount of charge that flowed, Q, multiplied by the electrical potential energy, hill, delta V, the potential energy difference, the electrical potential difference that charge flowed down. So that product, Q times delta V, is the amount of electrical energy that we've released as the current flows around the circuit, say through a resistor, and the resistor gets warmer. The rate at which energy is supplied, that's called power. So this symbol here, P, is for power. The rate that energy is supplied is the amount of energy we supply divided by the elapsed time. Well, if I divide Q times delta V by the elapsed time, by the time, Q over T, charge per unit time, is current. And so the power supplied to the circuit is the current multiplied by the change in electrical potential. So these are two very handy and really rather simple equations, that the energy supplied is Q, charge, times the voltage, and that the power is the current times the voltage, that describe the electrical power, the electrical energy that's being supplied by a battery to a circuit. So they're very simple equations that just involve multiplying two quantities, either charge and potential or current and potential, to get the number of joules that are coming out of the battery, or the number of joules per second, watts, that are coming out of the battery. It's very handy in describing how the circuit is working from the perspective of energy. Okay, let's try and use this to solve this final example. just in case you don't know what a flashlight is, we have a demonstration, but it actually doesn't know. Apparently I don't know what it is because I can't switch it on. Okay, that's because I left it on. When I was checking before class to see that it was working, and I checked it was working, but I didn't switch it off, just like I do at home. And so when I actually want to use it, it's not working. But anyway, in a flashlight, we're told that in this flashlight, 0.1 amps flows for 12 hours. So I did indeed, even in the problem, it's fantastic. Even in the problem, I've left the flashlight on. I've left it on with a 0.1 amp current flowing, and I left it on for 12 hours. And we're told that that current is flowing from a 1.5 volt battery. There's a bunch of amazing things that you can calculate with this seemingly uninteresting information about what the battery was, 1.5 volts, what the current is, 1/10 of an amp, and how long you left it on. You can calculate all sorts of things. We can calculate the energy that was supplied by the battery over that 12 hours. We can calculate how much charge was delivered by the battery over those 12 hours. And we can calculate even how many of those unseen electrons move through the lamp over that period of time. So I want to do that. Because I'm a little short of time, I won't do it on the thing I can't remember the name of. We'll just do it on the screen here. First part of the problem, A over here upstairs, or A over here down upstairs too, is to calculate the power and then the energy that was supplied by the battery. If you know, and this is often the case, if you know the voltage that the battery is supplying, right, it's a 1.5 volt battery, and you know that the current that is supplying, this was supplying 0.1 amps of current, that is sort of immediately telling you the rate at which energy is being supplied, the power. All you've got to do is multiply the known current by the known voltage, and that gives you the power, the number of joules per second, or watts, that the battery is supplying. So that battery is supplying 1.5 times 0.1, that's 0.15 watts, 0.15 joules per second. Well, if you know that the battery is supplying 0.15 joules every second, to get the energy, the electrical energy that's supplied, let's just multiply the power by the length of time that the battery was supplying that power. So I took the 0.15 joules per second, multiplied it by, this is the number of seconds in 12 hours. Is it 12 hours? I hope it is. This is the number of seconds into 12 hours, so I multiplied by 60, and then multiplied by 60 again, and I got this number here. This is the number of joules of energy that is supplied in those 12 hours. It's actually an enormous amount of energy, 7,000 joules almost. It's a large amount of energy. It just dribbles out of that battery, 0.15 joules each second. But you know, if you wait 12 hours, that's a lot of energy. Once you know, okay, so that's the question about the power and the energy, and it was easy to get knowing the current and the voltage of the battery. The second part of the problem was how much charge flowed around the circuit and how many electrons flowed around the circuit. That's also not hard to get from our understanding, our picture of what current is in terms of charges flowing. So if we want the charge that flowed around the circuit, and we know the current that flows through the circuit, just take the definition of current. Remember, it's charge divided by time. It's the amount of charge per unit of time. We can turn this around for the charge, which is what we want to find, in terms of the current. We just got to multiply the current of 0.1 amps, or coulombs per second, by this number of seconds in 12 hours. I did it. It's 4,300 coulombs, an enormous amount of current. Charge. That's the amount of charge in a thunderstorm. Finally, if I want the number of electrons, well, this is the relationship for the number of electrons. The charge that flowed is the number of electrons multiplied by the charge of a single electron. we know the charge that flowed, we know the charge of an electron. If I take one, the charge that flowed, divide it by the other, the charge of an electron, that gives me how many electrons went round the circuit. About 10 to the 22. An enormous number of electrons were pushed around that circuit. Okay, I'm going to finish there. We talked all today's class was about electrical current, about how we understand